Now I'm going to invite to the stage the Senior VP Academic to introduce our STAG lecturer of 2022. Thank you, Phil Wright.
Thanks very much, and thanks for giving me the opportunity to introduce our speaker this afternoon. Professor Peiris is unquestionably one of the premier astrophysicists of her generation. Hailing originally from Sri Lanka, Professor Peiris has held fellowships and positions at many prestigious institutions and can now be found either leading the UCL involvement in the Quantum Simulations for Fundamental Physics Consortium and the UCL Cosmoparticle Initiative, or at the Oscar Klein Centre in Sweden, of which she was director from 2016 to 2022, where she leads the European Research Council Advanced Grant Project Cosmic Explorer. Swedish involvement in the Vera C. Rubin Observatory's Legacy Survival of Space and Time, as well as the Axiom DM to further Axiom dark matter research. Professor Peiris has made clear contributions to our progress in understanding the universe and continues to push the boundaries of exploration beyond our standard model of particle physics. Her work crosses the boundaries between observational and theoretical disciplines, leveraging the power of modern astronomical data in the search to understand fundamental physics. In addition to her many notable achievements, she played key roles in observing the cosmic microwave background with the WMAP mission, which dramatically improved our understanding of the basic characteristics of the universe, and more recently as a member of the Planck mission, which mapped primordial fluctuations with exquisite precision. Professor Peiris has been recipient of several important awards recognising her contribution, including the Eddington Medal of the Royal Astronomical Society, the Max Born Medal of the German Physical Society, the Göran Gustafsson Prize in Physics, the Fred Hoyle Medal of the Institute of Physics, the Gruber Cosmology Prize twice, awarded to both the WMAP and Planck collaborations, and the Breakthrough Prize in Fundamental Physics awarded to the WMAP science team, and the Buchalter Cosmology Prize. In addition, Professor Peiris has made and continues to make important contributions to the UK science community as Vice President of the Royal Astronomical Society from 2016 to 2018, and she's now on the STFC Council, the Senior Strategic Advisory Body of the Research Councils that funds particle physics and astronomy in the United Kingdom. It's a great honour to welcome her here to Southampton this afternoon and to present this year's STAG lecture. So welcome.
Hi, can you hear me? All right. Okay, so I'm going to talk about the universe as a detective story. And I hope that there are many young people in the audience. And sometimes when you hear about science, it comes across as a bunch of facts. Everything's settled, everything's known, but that's not how doing science is like. And as we go through this story, I hope to convey to you the process of doing science. Okay, so let's get started. So I'm a cosmologist. So cosmologists study the origin, the evolution, and the fate of the universe. You know, just the small stuff. So cosmology is one of the oldest branches of science. And for the very longest time, it was a very speculative subject. You can see here the so-called Flammarion woodcut. And there is a medieval person depicted there trying to pierce through the dome of the sky to work out what makes the universe tick. You know, what's behind all these lights in the sky. And cosmologists today, to some extent, are still trying to do that. What we do is very different from all the other experimental sciences because we can't go and make a universe in a lab. I hope you agree that's probably a good thing. We can't make a universe pop into being, poke it a little bit, you know, change a little thing here and there and see what's different. We can't do any of that. So we have to do something else. We have to adopt the methods of detectives. So we have to look for the clues that the universe itself has left us and try to piece together a story about what the universe makes, how to make it work. And it seems that nature has been very kind to us. Nature has left us clues that express themselves in the language of mathematics and displays itself to us in the data that we can get from looking deep into space. So one of the reasons that this is possible is because light has a speed limit. You know, this is a bane of science fiction writers everywhere. Light has a speed limit. It's very fast, but it's finite. So that means that even the light from the closest stars takes, many years to reach us. So when we look at them, we see them as they were in the past. So you can repeat this exercise. And so observing the distant universe is a form of time travel. If you take one thing away from this talk, that's the concept to think about. When we look out into the depths of space, we see the universe as it was in the past. So eventually it starts to look quite different from how it looks today. It looks, simpler, darker. And eventually you get to the very earliest light you can see in the universe. And we call this the cosmic microwave background. I'm going to start by rewinding all the way back to 13.8 billion years ago when this light came into being. So let's start our story with the dawn's ancient light. But let's first remind ourselves that we live inside a galaxy. We live inside the spiral arm of the Milky Way. And so many of the maps that I'm going to show you are taking the whole sky and sort of opening it out into an elliptical projection. So when you see this kind of map, you're seeing the whole sky just in this projection, right? And if you look at the different wavelengths of light, you can see eventually as you go to longer and longer wavelengths, what the sky looks like in the microwave. So these are microwave frequencies. And if you then turn up the contrast by a factor of about 100,000, you see a picture like that. So that's a picture of our sky in the microwave. You see this red band across. So that's our own galaxy. So our own galaxy emits in the microwave. And if you look above and below that, you start to see these mottled patches of blue and green. So those are tiny variations in the temperature of the early universe, which also trace tiny variations in its density at very early times. And this is the imprint of everything that we see in the universe today. This is how it started out, as tiny ripples of variations in density from place to place that then grew under the action of gravity into everything you can see in the universe today. So a galaxy or a planet or a person, everything started out as primordial ripples in the early universe, where it was slightly uneven in density from place to place. So that is the beginning. And I'm going to lead you through the history of how we discovered this light. And also, how can we learn something about the universe from it? So to start at the beginning with its discovery, it was discovered by accident by two people, these two blokes, Arno Penzias and Robert Wilson, in 1964. They built an experimental radio telescope in Bell Labs in New Jersey. And they didn't set out to discover the origin of the universe. They wanted to do something far more mundane, which is to measure the emission from interstellar gas between stars. And so they turned on the telescope and they heard a hiss. And this hiss was coming from all across the sky. They couldn't work out what it was. They thought there was something wrong with their instrument. They started getting very obsessed about pigeon droppings. They very delicately called it a white dielectric substance. They got into the telescope, they started scooping the stuff out. Hiss didn't go away. And I've actually learned that there is a real murder mystery here. We know the culprits. Pigeons, they home. If you take them away from their nests, they come back. So eventually the pigeons were shot. And the hiss continued. They gave their lives in vain. and the hiss continued. So eventually the guys went down to Princeton University and they talked to their colleagues who had actively been looking for this hiss. You know, this noise instrument was basically the afterglow of the Big Bang itself. It had been predicted in the 1940s, and their colleagues were looking for it. These guys, found it by accident, and the pigeons didn't get anything, but they got the Nobel Prize for their trouble. So now I'm going to fast forward through a lot of blood, sweat, and tears, hopefully not blood, to 1992. Okay, so by this time, our instruments had improved enough that we could put a satellite into space and measure this radiation much more accurately. So this satellite was called the Cosmic Background Explorer, or COBE. It made a map that looked like this. Doesn't look very interesting. You see that the microwave radiation is very uniform all over the sky. So it worked that out. It also measured the temperature of that radiation. And it was just above 3 degrees above absolute zero. So very, very cold radiation, very uniform across the sky. But then it also made an extraordinary discovery. So you see, this is the first image of the primordial ripples, the tiny, tiny ripples, 1 part in 100,000 in the cosmic microwave background. It's a very crude image, very low resolution compared to the data we have today. And you see the red band across, that's a galaxy. But above and below, you see variations in its density. And so this is the discovery image of the origin of all the structure in the universe. I want to start to show the human face, behind these experiments as well. So Penzias and Wilson, just 2 guys built their own experiment, turned it on, made a groundbreaking discovery, Nobel Prize, done. Nowadays, the detective work is much more challenging. It's much more subtle. So we're starting to see teams of people coming together. And this is a theme that I hope you will take away from this talk as I go along, about how it takes the collaboration of many people with different skills to make these discoveries. So this is part of the COBE team. I very much enjoy seeing these pictures of some of my colleagues in these 80s costumes. On that side, we see George Smoot. Maybe he's celebrating his Nobel Prize, but he loves life, so this might be something else. There's also John Mather here, who also got the Nobel Prize for this discovery. And behind them, there's probably people in this room that do not recognize that that is a computer. Okay, so this is another theme that I'm going to keep returning. Computers make an extraordinary contribution to the way that we do cosmology now in order to make breakthrough discoveries. So they're increasingly playing a fundamental role in the process of the cosmological detective work. And I'll return to that theme later too. So in 2003, a 2nd-generation satellite launched by NASA delivered an enhanced view of the cosmic microwave background. This is the Wilkinson Microwave Anisotropy Probe. Try saying that fast several times. We call it WMAP. The satellite enabled a big increase in sensitivity and resolution over COBE, and the map came into sharp focus. So with the help of this new map, we were able to piece together what's called now the standard cosmological model. Okay, it is a model that basically describes all the data that we have obtained to date about the universe, and I'll get to it in a little bit. First, I want to show you some of the WMAP team as well. This is a very important picture for me personally because I'm actually there. This is during my PhD. You can see us looking very, very happy. That was the day that we had obtained the first version of the cosmological results from looking at the first map that we made. And on the right, you can see Dave Wilkinson, who's a brilliant cosmologist who sadly passed away shortly after that. And so the satellite was renamed after him. So now I want to talk to you a little bit about what we're seeing when we see this light. the early universe was very hot. It was so hot that electrons were separated from their nuclei, and the universe was filled with a hot soup of ionized plasma. Particles of light, which are called photons, couldn't really get very far because they kept bouncing off of the sea of free electrons. And so the universe was opaque to light. As the universe expanded, it cooled, and eventually, when it was about 3,000 degrees Kelvin, neutral atoms formed. So 3,000 degrees is very, very hot, but neutral atoms can stably exist at that temperature. So then the sea of electrons vanished into the atoms, and the light was freed. And the light has been traveling to us ever since through space. That's the cosmic microwave background. But why is it in the microwave? So in the early universe, where it was very hot, it wasn't microwaves. It was very energetic photons, gamma rays, X-rays. But as they travel through the universe, they share in the expansion of the universe. Their wavelengths get stretched out to different frequencies, longer wavelengths, and then eventually, now we see them in the microwave. The lonely journeys of these messenger photons are just remarkable to contemplate. They were released 380,000 years after the Big Bang. I mean, you might think that sounds like a very long time, but the universe is now 13.8 billion years old. So this was at a time when the universe was essentially like a baby, right? And in that intervening time, these photons have traveled to us without interacting really with any other matter till they were eaten by our detectors. So they actually paint a pristine picture of the conditions in the early universe. And also, this should give you the idea that the universe is extremely empty. So that is the story of how the light was released to come to us. And when we look at it, the pristine picture that we see is a cosmic tug of war. It's a battle between pressure, which tends to push things out, and gravity, which tends to make things fall in. So this sets up sound waves in this primordial fluid. And we see the sound waves frozen at the time that the universe became transparent to light. Okay, you can also hear the sound of the universe when it was very young. We can take this map and we can convert it into sound and we can listen to it. So you can actually hear that this is not just one frequency. You can hear that there's structure in the sound. So deciphering the meaning of that structure is what allows us to work out what the universe is like and what are its properties. So how can we learn anything from this data about the universe? So in addition to the beautiful instruments that allow us to measure things about the universe, we also have theories that make predictions about what the sky should look like. So remember, we can't do experiments with the universe. However, we can calculate precise predictions for what the sky should look like under different physical theories, and they look different. And so this map is like a fingerprint, and by comparing the theory predictions with the fingerprint that we see on the sky, you can read out theories that don't look like the sky and keep the ones that do look like the sky. So here again, the advent of computers is very, very important. We need to calculate what this fingerprint looks like millions of times on a computer, and that usually requires a huge amount of supercomputing power. So when we do that, what we find is something rather surprising. So the map made by WMAP was about a 3 megapixel map, and all those thousands of pixels are described by just 6 numbers. So these 6 numbers tell us the shape of the universe, its clumpiness, It tells you the constituent components, the atoms, dark matter and dark energy, and when the first stars formed. And it also tells you the age of the universe. So using this map is how we precisely measure the age of the universe. So the model of the universe that describes the data is surprisingly simple. However, this simple model contains 3 ingredients that are not part of the standard model of particle physics, which describes everything we know about matter. So there's dark matter and dark energy. The standard model of particle physics doesn't contain those. And also we know that the early universe was slightly clumpy. Otherwise, we would not have any structure in the universe today. So what made that clumpiness? So these 3 ingredients are not in our standard theories of physics that has been tested in the laboratory. So the message that this data is telling us is surprising and strange. So it's time to take stock. I'm now going to rewind the story that we have learned from analyzing the data from WMAP and show you the history as we understand it after WMAP. We're going to zoom into a cold spot in the primordial soup. That's the place where there's more matter than average. And matter is attracted to matter by gravity. And as chunks of matter start coming together, recognizable structures start to form. The universe is a dark place till the first stars turn on. Matter evolves into sort of filamentary structures. They're traced by galaxies. And we're looking through all this intervening turbulent history into the very pristine early universe. Now we come to Planck. Planck is a European Space Agency mission, and it was launched in 2009. Planck, being the 3rd generation CMB satellite, was on a different scale of complexity and sensitivity and ambition from previous CMB experiments, both in the terms of technology and also the number of people involved. So you see now the teams have evolved into much larger sizes. The success of this mission is a testament to European cooperation and the collaboration of scientists from all over the world. Planck operated way out beyond the orbit of the moon. WMAP was also there. Currently, the James Webb Space Telescope is there as well. Planck's detectors could measure temperature differences of a millionth of a degree. And that's like measuring from the Earth the heat of a rabbit on the moon. To achieve this, some of Planck's detectors were cooled to about 1/10 of a degree above absolute zero, so that their own heat did not swamp the very delicate signal from the sky. That's colder than anything in nature. So as a result of now a 50 megapixel map from Planck, the baby picture of the universe sharpened yet again. And we measured cosmological parameters to percent precision. So here's an example, Planck's measurement of the age of the universe. So it's 13.82 plus or minus 0.05 asked since the beginning of history with 0.5% precision. Now I want to rewind time even closer to the beginning. So now data of this quality allows us to answer one of the more audacious questions that I posed at the start of the talk. So the precision of Planck allows us to rewind time back to an instant. So this is a decimal point followed by 32 zeros and a 1, a tiny fraction of a second after the Big Bang. This takes us tantalizingly close to figuring out who done it. Where did all the stuff in the universe come from? So at this very early time, we think that quantum ripples in a so-called scalar field, we call it the inflaton field, seeded all the structure in the universe that we see today. So during the same infinitesimal this inflaton is thought to have caused the universe to expand extremely rapidly by a factor of about 10 to the power 26. This is a process we call inflation. This is not what's happening to the economy today. This is what happened to the very, very early universe, we think. So the universe grew so fast that light itself could not keep up, and the observable part of the universe became flat and smoothed out initial inhomogeneities. But at the same time, tiny quantum ripples within the scalar field were stretched out by the expansion of the universe and became all the seeds of structure that we see today. Then, 380,000 years later, you see the imprint of those same ripples in the cosmic microwave background, starting the story of the universe I presented to you a couple of minutes ago. This idea that everything in the universe arose as tiny quantum fluctuations can sound like science fiction. Through the discovery of the Higgs boson by the Large Hadron Collider, even the concept of a scalar field was completely hypothetical. But now we know that nature contains at least one scalar field. However, inflation is still a very big extrapolation of laboratory physics, a sort of here be dragons period in the history of the universe. So how do we test that this idea is correct? This theory is a big extrapolation from laboratory physics, but it has the virtue of making precise predictions. For example, it says that the power of CMB fluctuations should be distributed as a function of wavelength in a certain way. So let's try to get some intuition about this using an analogy with sound. You can think about the information in this map in analogy with listening to a piece of music and trying to figure out whether the music is, bass heavy or treble heavy. Okay, so the very largest scales in the universe are the longest wavelengths. So that's like being bass heavy. And short length scales are the treble frequencies. Using the map, we can work out whether there's more power in the bass or the treble. And the theory of inflation makes a precise prediction for what you should see. So imagine that there was more power in the treble compared to the bass, so a treble-heavy universe. Maybe that would sound a bit like this. It's a very, very peaceful universe. If the universe had more power on the large scales compared to the small scales, it will sound like a bass-heavy piece of music, like this. Hello? Oh. And if the universe roughly had equal power across the frequencies in large scales and small scales, it would sound like a more balanced piece of music, like this. Thank you, Mr. Bach. So Planck has precisely measured that the universe sounds roughly balanced, a little bit bass heavy. That's exactly what inflation predicts. So inflation was not the only suspect in town for explaining the origin of structure in the universe. There were other theories, such as cosmic strings. These are one-dimensional defects in space, or textures, which are like swirls in space. These theories also made very precise predictions for what the CMB sky should look like. The data did not look like those predictions. So these suspects were eliminated from the inquiries of the cosmological detectives. People worked on different kinds of theories for many years, sometimes entire careers. And then the data came in and told us the answer. And some of those theories were wrong. Here, I want to make a really important point, which is that looking and not finding is not the same as not looking. You have to test theoretical predictions with the data. And if the theory that you worked on disagrees with the data, your time has not been wasted because you've still learned something. You've learned that the universe works in one way and not in another way. This is extremely valuable information to the cosmological detectives who are trying to extrapolate well beyond laboratory tested physics. So now I want to talk about the dark side of the universe. So let's turn to the very bizarre fact that the universe is mostly stuff we cannot see. So matter made of stuff like us, and all the matter described by the standard model of particle physics is only 5% of the universe. 80% of even just the matter in the universe is not that kind of matter, it is dark matter. But matter is not even the dominant component of the universe at all. That's dark energy. So it might sound like we don't know what we're talking about and we're just calling things dark. If you say that, you might actually be right, you know. We're talking about ingredients whose effect that we can measure based on their impact on the stuff that we can see. But these components do not fit into the standard model of particle physics. We have more idea about what dark matter could be than what dark energy could be. You know, there are many extensions to the standard model of particle physics where, you know, you can get candidate dark matter particles, which very weakly interact with normal matter, so they're very hard to detect, and yet that can provide all of the matter density that we need to make a universe like ours. So that might be easier to explain than dark energy. Dark energy is a very different beast. It's making the expansion of the universe accelerate. Just like the universe seems to have done at the beginning, it's now accelerating in its expansion again. It's been doing that for 1 billion years and it's not going to stop. This is expected to lead to a cold, sad end to the universe many, many billions of years from now. So don't worry about that. Worry about climate change instead. But that's the fate of the universe that we've worked out. It's very sad. But we don't know what dark energy is. We can only measure its effect on the universe. Dark energy is here bedragon's territory again, and we'll characterize its impact on the universe better and better in the coming years. But understanding what it is will require, in my opinion, a breakthrough in theoretical physics. However, we can probably learn a lot about what dark matter is in the coming decade. And so now I'm going to talk about that. So an obvious way to view the universe is in the visible light. There's a reason that our eyes have evolved to view the world at optical wavelengths. The sun has a significant radiation output at those wavelengths. So starting in the 1990s, we've been mapping the universe in starlight in very deep and large-scale galaxy surveys. So this is part of the Sloan Digital Sky Survey. This is not a simulation. Every one of those galaxies is a real object. There are about 400,000 galaxies in this animation. I could stare at this for hours. It's like a swarm of fireflies flying through space. You can see that they're clustered. They congregate. They're not scattered randomly in space. Why do they congregate? It's because they're tracing huge filaments of dark matter that you can't actually see. You cannot see 80% of the matter in this image. This is a slice through a simulation. that shows you how galaxies trace dark matter. When you see this image, it might perhaps remind you of seeing pictures of the Earth from space at night. So before the invention of electricity, if you looked at the Earth at night, you probably could not work out where there were oceans, where there were continents, and so on. But now that we do have cities and we have electricity, you can probably look at the Earth from space at night and work out the outlines of the continents. And you can see that there are land masses. This is, of course, a biased measure. It basically does not trace where the land is, it traces where people live. You're probably not going to make out Antarctica, for example. Similarly, galaxies trace the underlying scaffolding of dark matter in a biased way, and we can simulate how they populate these dark structures. So this is such a simulation. Again, you can see the utility of computer simulations in cosmology. This is a simulation of the formation of a cluster of galaxies. Galaxy clusters are the largest structures in the universe. They're very massive multiplexes of galaxies. They blow out huge plumes of gas as they form and eventually start to look like the clusters that we see in the real universe. So how can we use this kind of work to figure things about dark matter? It's a little bit about, it's similar to how we figured out the standard model of cosmology. Using computer simulations, we can make detailed predictions for the fingerprints of different kinds of dark matter, which will alter how the galaxies are scattered in the scaffolding of dark matter. By extracting how those structures look at different wavelengths in the simulations and comparing them to the data, you can figure out which of those theories match the data and which should be discarded. So this is research currently actively underway. This research requires a lot of supercomputing power. You might remember that when I showed you the Colby detectives back in the day, there was a little desktop computer behind them. Nowadays, we use supercomputers like this. We run huge computer codes and make precise simulations of what the universe should look like. But on top of that, our data sets are now getting so big that we need completely novel methods to extract information out of that data. A human being could sit there and spend an entire lifetime looking at the data and only be able to look like a tiniest fraction of it. It is big data and it needs big algorithms. So I'm currently working very hard preparing for the ultimate big data project. This is the Vera C. Rubin Observatory. It's starting operations in a couple of years. Rubin will carry out a 10-year survey of the universe. The pictures of the universe I've shown you so far are static. They're frozen in time. Instead, Rubin will return to every patch of the sky, roughly every 3 days or so, take pictures, and do that for 10 years. So by stitching those images together, we will make a movie of the universe. This will enable us to study space and time in a way that was never done before at this scale and enable diverse science missions at the same time. Rubin will create a deluge of data, and different communities have come together to try to make sense of it. These include not just cosmologist detectives, but also computer scientists, data scientists, and statisticians. We are all joining together to try to make sense of this data and extract information from it. So now remember the theory called inflation, where the universe created all of the structure in it from tiny quantum fluctuations at a very early time. So this theory makes an extra prediction. If inflation happened, it should have set the whole universe ringing like a bell. The resulting ripples in the fabric of space are called gravitational waves. So there are many different types of evidence that we can seek as cosmologist detectives. There's the absence of evidence, which kills theories. there is circumstantial evidence. For instance, the type of evidence we've accumulated so far, which makes us think that even though inflation is a strange, exotic idea, it may capture something about the nature of reality. Then there is smoking gun evidence that would demonstrate beyond reasonable doubt that we are on the right path. Gravitational waves from the primordial universe would present such smoking gun evidence in favor of inflation. So this is very exciting because there's an avenue to actually find the smoking gun. That's because the cosmic microwave background is polarized. That means that the light that makes up the cosmic microwave background vibrates preferentially in a certain direction. The texture on these maps indicates the preferential direction in a sort of visual texture. I love this visualization. Oh no, it's going very different from what I'm talking about. That's very odd. It hasn't changed. Oh, this was the texture, sorry. And now it's completely mismatched with this. So I hope that I don't get this wrong. But, you know, it's like, you know, I love these colors. It's like a Van Gogh image, right? So if there were gravitational waves, it would make a tiny, tiny change to the pattern of this polarization on the sky. And so, you know, that would allow us to detect directly the smoking gun evidence. But this is a very, very difficult measurement to make. And you must make it from very cold, dry, high places on the Earth, like Antarctica. I actually have friends who winter over in Antarctica, spending many months in the dark working on telescopes because they're really keen to find this signature. See if this works. No. Oh, here we go. So I remember, now remember this theory called inflation, which, so I did talk about this, didn't I? Yeah, I did. Yeah. Oh, no. I knew this was going wrong today. Yeah. Oh, it's the same. Okay, good. So we talked about this. No, it's wrong. So the problem is that my computer is not the one that's showing the screen behind me. So let's wait till this is fixed. So that matches what I see now. Can I go forward? No, it's missing one slide. Oh, gosh. All right, I'm sorry. Usually it's easier to look at you and not back there. But so basically, what does this have to do with black holes is what I was going to talk about. Okay, so, you know, there was a time when we did not know that the universe could make gravitational waves. However, in 2015, we actually worked out that it could. And why was that? Because in the distant universe, two very massive black holes merged together, and it actually, you know, merged into one, and that led to a huge burst of gravitational waves, and it basically converted the mass of 3 suns into gravitational wave energy. These waves rippled through space, and in September 2015, they reached the Earth, and they made a tiny, tiny change, a fraction of a size of a proton in a mirror in an observatory called LIGO. So LIGO is one of the most amazing things that has been built by human beings. So, you know, to be able to actually detect this tiny, tiny change, a fraction of a proton in the position of a mirror, it spent the first 25 years of its life measuring noise. So imagine, a career in which 25 years of your work is spent measuring noise better and better, till you can detect waves crashing on a rocky beach, till you can detect the engines of airplanes flying overhead, measuring noise so that you can characterize and understand it so well, so that when you see the tiny signal from a gravitational wave, you know that it's real. They actually have two of these detectors so that they must coincidentally detect these signals so that you can discriminate it from something that's happening on the Earth rather than something happening on the sky. And so that's what happened at LIGO. So now we know that the universe can make gravitational waves. So that's also something you can listen to. Hopefully you can hear that signal. And that is the discovery sound of gravitational waves. So this is also very, very exciting for cosmologists. Just like electromagnetic waves, gravitational waves can have different wavelengths. And by changing the size of your detector, you can detect waves of different periods. So LIGO detects sources like black hole mergers that produce waves with periods of roughly milliseconds. Now, if you scale this up in the coming decade, we're going to do so. You can get to, say, 3 spacecraft flying in formation around the orbit of the Earth. So now you got a detector the size of the Earth's orbit. That's an observatory that's going to be launched sometime in the future called LISA. Then you can detect waves with periods of minutes to hours. That makes you sensitive to very, very massive black hole mergers, millions of masses of the sun merging in the hearts of galaxies. Then you can use as a natural laboratory a network of pulsars. So pulsars are spinning neutron stars, dense spheres of exotic nuclear matter, and they're the size of London. The mass of the sun squished in the size of London. Okay, so that's like a natural laboratory to try to detect gravitational waves. And to tie this back into the origin story of the universe, the gravitational waves produced by inflation would have periods of billions of years. It's the size of the universe, right? And to detect that, you have to use another natural laboratory, the cosmic microwave background. So in the last couple of minutes, I want to show you a mind-blowing implication of inflation. If it's a correct description of nature, inflation doesn't just make the observable universe. It makes a big universe, much bigger than that. And even more bizarrely, that's not the end of it either. It will create a structure on huge scales compared to the observable universe. It will create other universes, bubble universes, with our universe just being one among innumerable others. So that's the implication of this theory. It sounds like science fiction. But this implication is something we have to grapple with and find a way to test it if the clues continue falling into place and pointing the finger at this theory. So by definition, it's not going to be possible to test predictions for what happens outside our own universe by studying data from inside our universe. We can't make universes in the lab either, sadly. So one way that we have been exploring this implication of the theory is to emulate the same physical equations, but translated within an analog experiment in the laboratory. It's a condensed matter experiment that actually uses something called Bose-Einstein condensates. It's very, very cold atoms, where phase transitions in the laboratory can be measured and compared to the predictions of the analog equations that predict phase transitions in the early universe. So a phase transition is like the birth of a bubble universe. you, I think, understand what phase transitions are. If you boil your kettle for tea in the morning, you have liquid going to gas via the formation of bubbles. So that's what we think happened within the very early universe, when the universe translated from one vacuum state to another. So at least if we can test that the equations are valid and predicting something about reality in an analog system, we can be confident that the extrapolation of theoretical physics that has this startling implication of a multiverse are actually accurate. So a prototype experiment like this is being built. So watch this space. I might be able to come back and tell you what happened later. So this is a modern version of the Flammarion woodcut that I started the talk with. We've learned a lot. We've been able to answer some questions that people have been wondering about since the dawn of history. We have found that the universe is both simpler and much stranger than we ever imagined. We found our origins deeply tied with the quantum world. We have looked at, listened to, and felt the universe giving us clues to our origins and our fate. So often, as I said at the start, when one learns about scientific breakthroughs, someone's getting a Nobel Prize, everything's settled, everything's so certain by the time that happens. I hope hearing about the process of these discoveries actually conveys a better story of what doing science is like. There's a lot of lead time into making these experiments work. You know, whole careers can be spent working on theories that turn out not to correspond to reality. There's audacity in that. There's courage in that. People can be wrong. There can be many blind alleys, but the scientific process itself is self-correcting. There's a lot we don't know, and there are very simple questions that a child can ask about what I presented today, where I have to be honest and say the answer is, we don't know. So rather than being a collection of facts, this is the process of exploring into the unknown. By using the methods of detectives, we will hopefully work out the story of the universe in more extreme regimes, further back in time, and also into the distant future. Thank you very much.
Well, thank you very much for an amazing talk. Okay, we're going to open the floor to some questions for a few minutes. We'll also be hearing online. Where's Omar? Maybe he's gone. He's over there somewhere. Thank you. Okay, so anybody in the audience wants to ask a question? Who wants to be brave and ask it first?
I love questions. Come at me.
Oh, there's a roaming mic. Thank you.
The way you describe the cosmic microwave background sounds as though there's a peak of radiation. What caused it to fall off?
I see. So what you're seeing there, literally, there is a peak, okay? It's about the size of a degree, right? So what causes it to fall off is the fact that the width of that transition is finite, right? So if this transition could be seen at all times and it was not finite, then you would see essentially, you know, a sine wave, right? So what cuts it off is the thickness of what we call the last scattering surface that made the universe go from being completely opaque to, you know, completely transparent. Sure.
Anybody else?
I'm a simple person, not a scientist. What surprised me most, I think, about your talk, which I thought was excellent, thank you very much, was your surprise at the idea of multiple universes. It has long seemed to me, as a simple person, that nature is quite remarkably free of singularities. There are very few things in nature that only happen once, if ever, if any, rather. And I think the same is true of cosmology. There are no type of star that's only been observed once, I think. So why the surprise that the Big Bang would be a singularity?
So in this picture, actually, one of the nice things that it does is to remove the Big Bang from being a singularity. It just becomes a coordinate singularity when viewed with a particular general relativistic metric. But in another sense, there's no singularity at all. It is just the birth event of the bubble universe. So actually, you know, that aspect of it, it removes the singularity. It actually is very attractive. I think what causes the surprise is the fact that we keep learning the universe is bigger and bigger and bigger than what we imagined. And that's always very surprising, I think, to us humans, because we are so tiny and we like to still think that we are very important, right? So even 100 years ago, we didn't really know that there were other galaxies other than the Milky Way. We've gone from that to learning that there are millions and trillions of galaxies. And still, you know, making other universes exist in your mind seems very difficult to people. I mean, I personally like this idea, but I want to test it because it is a big extrapolation of physics. Some theoretical physicists really like this idea because it's an implication of their theory, so they were not surprised by that. But people that work with data are very conservative, and I think that it is very right that they want to test such ideas.
Great. We have a question online.
Yeah. Why does the Milky Way appear red in one of the first pictures you showed?
That's a good question. So it depends on what frequency that you're emitting at, right? So the picture is, of course, color coded, and the red is supposed to correspond to a particular frequency in the range of microwave frequencies. That's all, right? It emits in that band, in that particular visualization. If I took the same picture at different frequencies, the shape of the Milky Way and its extent away from the plane will change. And that's exactly how we remove the Milky Way from the data to get a pristine picture, right? We take many different frequency pictures and we subtract out the wavelength dependent part.
So following up on this question,
Yes.
so the Milky Way was also emitting microwave radiation, right? So then you basically subtracted that radiation to get the full picture.
Yeah.
Okay, thank you.
That's right. And the underlying thing is that the cosmic microwave background has a particular temperature, is very well measured to be one temperature. So it doesn't change much as a function of frequency in a certain way, but the Milky Way does, and you can take it out by measuring that frequency dependence.
Have you got all the information you can use from cosmic microwave background, or would extra resolution give you extra information?
Yeah, just to repeat the question in case there are people didn't hear it, can we use more data on the cosmic microwave background at extra resolution and sensitivity? For the temperature of the cosmic microwave background, just mapping out temperature variations, we basically saturated the information, but the polarization signal that I was trying to present to you while the technology was failing, that has to be investigated in much more detail. And there, that signal is much fainter than the temperature, right? So we are still in the process of mapping that out. And we are going to do that both from space and from very cold, high places on the Earth, like Antarctica and Chile. So that research is underway. And in particular, there is an observatory called Simon's Observatory, which is going to be the next major step in that area. And the UK has just invested and bought into that experiment so that we can get that data and we can work on it in this country too.
Sorry, I've already been given the mic. So you showed that the universe is 13.8 billion years old, according to the cosmic microwave background, but measurements of the local expansion rate give something different. What are your thoughts on that?
So measurements of the local expansion rate by itself cannot tell you the age of the universe. You have to assume a model for extrapolating it, right? But indeed, you're right that there are signs that there is a cosmic tension, okay? So we can measure the properties of the universe fully in the early universe. We can measure all the parameters of the universe, and then we can extrapolate it forward and say, how fast should the universe be expanding today? Right? So that's a very precise prediction. And if you then try to measure that rate of expansion today and compare it with the early universe measurement, there is a bit of a tension. So my opinion on this is that both data sets have been examined very, very carefully, right? And we have ruled out very obvious mistakes in either side. But I would still like for the local measurement to be corroborated by a completely different method. And that's because there's so much more astrophysics involved in making the local measurement. It's actually in some sense much harder than modeling the early universe and comparing that with our theories. So I'm going to give a diplomatic answer there. And I think that gravitational wave measurements could shed a new light there.
Okay, there's a gentleman there online and then a young gentleman over here.
Thank you. Thank you for a fascinating, very engaging speech, talk. Now, my understanding of the multiverse is simply that it is the collection of all possible universes and all possible parameter settings and histories, which is quite a lot. On the other hand, you reminded us that because of inflation, we have the vast majority of our universe is unobservable. And then you've told us that that is the locus of the multiverse. So which sounds completely different.
What was the last thing you said?
What I've understood you to say is that the multiverse is precisely the unobservable universe.
Okay. So there are like many different definitions of what a multiverse should be. I'm talking to a very precise definition, which is the implications of what we call eternal inflation. There is another type of multiverse, which is the branching out of timelines that's in the Everettian picture of quantum mechanics. That is not what I'm talking about. So basically, eternal inflation tells you that inflation only ever stops locally. So this process of making the size of the universe just balloon up in a tiny fraction of a second, that's called inflation. So eternal inflation says that, you know, it only ever stops within a bubble universe, and between the bubbles, the universe is still accelerating in its expansion, okay? So the problem is that we are a tiny bit, our observable horizon is a tiny bit within a bubble universe. And so we can't really access the rest of the sort of huge multiplex around us that the theory tells us should be there. There is one aspect of this which I think could be probed if very early on in their history two bubble universes collided. That would leave a bruise, a kind of change to the spatial structure of our universe that would also imprint in the cosmic microwave background. But the chance of that collision happening is actually very small. So we would have to be lucky for our universe to have undergone such a collision. But when this polarization data comes in, we are going to look for that signal. I don't know if that answers your question, but did you ask about that or something else?
Thank you. You simply clarified that there are multiple.
Yes, cool.
Great. Online question.
There's another question from the online audience. Roughly how long did it take for the universe to transition from opaque to transparent?
I don't know the number in units that the person might understand. It's a tiny fraction of in redshift, but I didn't want to talk about redshift. But in the scheme of things, in the scheme of history, this was instantaneous, essentially. Okay.
Right. There's a question from a gentleman around here. Oh, okay. Fantastic. Oh, it's okay. So everyone can hear.
You said that the universe will end. Will it not follow then that this is not the first or last universe? And is that a possibility? Like, how is it going to end?
How is it going to end? Sorry, but what was the first part? It was so loud that it just kind of blew my
You said the
brain.
universe is going to come to an end at some point. in the
Yes, it
future.
is. I see. There are many possible extrapolations of physics that we could talk about now. But if we take the simplest explanation for what is dark energy, which is that it is a cosmological constant, the universe is essentially going to become more and more and more dilute over time. So no new matter is being made, right? So if the space between galaxies starts being stretched out at some time, our observable universe may not contain other galaxies even, right? Because the observable horizon is shrinking during that period. And eventually, the stars will die out. Then there'll be a thin soup of stuff and some black holes. Eventually, the black holes will evaporate. Then there'll be a thin soup of radiation that's getting colder and colder and colder. So if I just take a bet saying this is our current scenario, then it could be that. It could be that, there is another vacuum state to transfer to as well. So we think that this bubble nucleation comes from the universe transitioning from one vacuum state to another. There might be a lower one we can go to. So we could nucleate a bubble universe within our universe, and the part of the universe would jump to that. All sorts of speculations which sound like science fiction and very difficult to test. So, if I'm around in a few billion years, maybe I come back and answer.
Okay, let's ask one last question. Gentleman over there.
Hi, based on the multiversal section earlier and also from a recent lecture, is it possible that the inflationary epoch began before the Big Bang? And if so, what are the implications of this?
So you are asking about a definitional question. So usually people mean by the Big Bang, the time equals 0 or the coordinate singularity in the multiverse picture, right? So it's the time at which the universe was very hot, etc. So inflation actually in that definition is before the Big Bang. It explains the initial conditions for the Big Bang, the hot Big Bang theory. This is a definition thing. So indeed, if eternal inflation is correct, time goes back infinitely. And, it becomes more and more unclear whether our understanding is right as you go back into the past. So I would say the hot Big Bang is very well established. Inflation is a hypothesis that has support behind it. Eternal inflation is a big extrapolation from that. And so as time goes to negative infinity, we know less and less.
Right. Okay. Let's thank Hiranya again. Right. Before we all depart, I've got some more thank yous to make. I want to thank the STAG committee themselves for being such stalwarts and helping arrange this. The events team, iSolutions, who I know have been working extremely hard, and especially Barbara Saiter. Barbara, say hello. Just stick hand. Thank you very much, Barbara. So a round of applause for everyone there. And in time-honored tradition, we have a gift for the speaker.
Oh.
Yeah, come back up. You've got to give another lecture now. Right. Okay, so this is a wonderful piece of art. We always do one for our lecturer. Thank you for Niels for organising Diwali. It's absolutely brilliant. So this is for you to cherish and look at yourself.
Oh, no. Oh, wonderful. Thank you.